Good afternoon. It's nice to meet everybody here on site and those who are probably listening in virtual reality. I'm really glad that we can meet on site, and we hope to be more and more often again, because it's nice to see your colleagues in face and see those who are listening, who are sleeping, or who are working with their computers. My colleague Zan. Yes. I will tell a little bit about our research on shared car process, car sharing process optimization. Well, let's start with that car sharing is nothing really new. First, tries to make some car sharing system was in 1961, as far as I know, in Germany, where it was a village where whole society decided, let's buy some 10 cars and we'll use them together. However, this area developed very fast, and today this car sharing service is rather different from that one. And today we know that we can take a car from mobile phone somewhere in the city, use it, leave it somewhere other side, and pay for this one-time rental. I can drive probably to Sofia and use car here, then go to another city, use it again, some other car. Well, this research were conducted by three, let's say, working in three organizations in University of Latvia, CRD Group, which is software developers, and the third partner is CRTC Pro, which is a car sharing service owner in Latvia. So we had really real-life test bed for this. About what kind of service I'm speaking. Obviously, it's car sharing. Then it's commercial, because there's a lot of researches not only about commercial services, but we are speaking about transport sharing. There's a lot about from community perspective, a lot of optimizations, and from public transportation, etc. We are speaking about commercial service. Then free floating. It means that there is no dedicated parking places for the cars. We can expect that whole city where, let's say, normally we are allowed to park our car, we may leave shared car. It means that it's free floating, and practically whole city can be expected as parking site. However, in the future we'll see that it's better to look at the system like there are a lot of parking places, not free floating. Okay, then there is one way. It means that you take car in one place, drive to another, and leave it. It's not like typical renting when you take car in one site, make your trip, and return back to the same place without ordering. And what does it mean? It means that we don't know future rentals. We don't know when they will start. Okay, we know 15 minutes ahead and reservation is done, but we typically don't know which customer, what time, where he will go, when he will return. When you rent car in some classic rental services, then you say, I will take on that day, that time, I will return after 3 days. Here, we don't know this. We just know that somebody probably will rent our car, and typically less than 24 hours, but even that is unknown. And we're speaking electric cars. It makes the system a little bit different from the other, because we need to charge. We need regularly charging of cars, and it's not like in diesel or petrol cars. It doesn't take 1 minute or 5. It takes 2 hours, maybe sometimes more. And with possibility of relocation, it means that there are some service employees who may relocate cars if they are left in some outer areas where car is not demanded, the demand of cars is not so high. They can relocate them to other more suitable positions. Taking all this in account, we can look at some problems which are most common and most, let's say, obvious probably, free floating. It means that cars may be left, as I said, anywhere, and maybe even in some very unexpected places. Further rentals are known, and we don't know exactly where's real demand. We can just try to predict it. And situation changes in real time. This means that even if we have some picture now and we have decided with service people, let's move this car to that place, it means that probably in that moment, that one car is already gone somewhere other place. How can we somehow intervene in this system by some technical processes? The first one is decide when to charge car. If it's somewhere in city with 30% battery level, do we need to recharge it now or probably do it later? When to charge it, and the second option is where to, when, and which car should be allocated. So those are these processes which are trying to optimize, because at the moment they are done by the allocation staff, by their personal experience, let's say by expert decisions. The first thing which we must do, and we decided to do, is, well, it's not exactly our decision, but it was a suggestion from other authors, because we studied a lot of algorithms. As I said, it's not the first, it's not something very new, and we just developed and extended existing algorithm, and I will mention it later. But the first thing is to look at city not as whole piece, but divide it in sectors, and we can look at each sector. This is Riga as one, let's say, parking site. And if you say, let's park it in Imanta, it's one of the suburbs in Riga, it means that it's okay if you park it anywhere there, because inhabitants will have, let's say, 200 meters to walk the car, it will be okay. And one more thing, that it should be that inhabitants of that area would have, let's say, the same habits. The rental intensity is the same, the income from the cars in the area is approximately the same. And here comes historical data, which we have in the system. Typically, if you have some car rental system which is running, there is historical data about rental experience. Then you can calculate, let's say, potential income for each of these sectors. And in our case, by potential income, we understand if car is placed in this site at the moment, how big will be the income, probability of income in next hour. And so we can rate all of sectors this way. Let's say it's not exactly evaluation of terms of euros, but let's look at like an index. The higher the index, the best the place at the moment. Potential index is higher. If you look at potential income value, of course it can differ from hour to hour, even from day to day, and there is this expected profit for one sector in different days, and you see that at the midday there is profit index rather high in weekends, but in other days it will be lower. So probably it's good to move cars there in weekend, but not in work days. Or the situation changes at the 16 to 12 o'clock. There can be difference between sectors, and there we can see in the same time how changes the profit, potential income, this index value for different sectors, different time. And we see even here sector B looks very good. At the end of the day, it's probably the same in this sector A. And based on this, we can try to decide where potential income will be the better and where it's better to place the car. Now let's go to the optimization model. As I said, it was extended version of other the location model. The first thing we tried to do is to look through models which we find in the scientific papers. There is, by the way, one very good research where many of those methods and models are described and, let's say, made some dictionary. It's in our paper mentioned, and there's one model which was based on many things alike we are using, but it was based on knowledge that we know for the rentals. Customers will, before they're renting car, they just mention, okay, I will go from that side to that side, and I will be probably for 3 hours. With this knowledge, it works rather fine, but we tried to make such a predictions from our database for the further rentals, but it didn't work so good. So we changed it a little bit and adapted from our case, from our solution. So objective for this MIP model is to try to maximize the potential income, which is rather obvious for those guys who are with high battery level, and we try to charge as long as possible car from those who are uncharged, and to make it in, let's say, some comparable economic value. There is index which shows this balance between those who are located cars and those who are charging. As output result, we get the location plan where for each time instance there is tasks for each relocator which says take that car, move that location. By time instance, we understand some time period, typically some 10, 15, or 20 minutes. It depends on the situation which you would like to use the algorithm. And we say, okay, let's make this plan for next 6 hours or 2 hours. And if this time slot is 15 minutes, and for 2 hours, there will be 8 time instances. So the plan will be created for 8 time instances. And the input data are city sectors. We know about each sector, is it possible to charge car there, and what's the maximum number of cars which you can park there. It's again data, not theoretically. We can try to compute it from historical data, but in our case we used expert data, and typically it wasn't more than 5 cars in one sector. Then we use rental history to calculate potential incomes for sectors. Available cars with their locations and battery levels, relocators and their locations, and the last but not least, time instances. How many time instances we should plan ahead. And as a result, well, there's just one small example of the plan, but the idea is like if there's yellow circles, those are relocators, green are cars, then, for example, here we can see that in the first time slot, relocator from here takes its car, goes here, takes another relocator, goes in second time slot here, takes this car, and then they both move here. Here's the relocator who's in second time. Well, it's like rather straightforward plan. Just read what's written in your script, just do it. As we know from previous lecture, it's nice to have some smart algorithms, but time is essential if you talk about big numbers. And here, optimization model must be calculated at some reasonable time, and we just make some calculation tests from the data we had from this our partner Fixie Pro, and well, we tried with different number of time instances, trials, sectors, or locations. Practically always we get some at least 10% potential income, expected potential income increase, and calculation time was to 6 minutes, and here's 15 minutes because it was set some time limit, and if we in calculation went higher than 15 minutes, then we got suboptimal result, and we worked sad. We tested our model in real life. We had this options, this opportunity, and it was great. And it was more not like to prove exactly that it will work. This and this good, but just proof of concept, but we can gain better result than it's at the moment in the specific system. We used car sharing company Fixie. To conduct this test, we built two separate groups of relocators. M team is manual, a automated team. Yes. They had separate numbers of cars, separate sets, approximately 20 cars in each. And what was very important that in the morning when the operation started, those 20 cars had average potential income the same. So they started approximately from the same base. And at the end of the day, there was evaluated all results, and typically it was number of relocations, average increase of potential income, then length of relocation, and of course, what was real income from all of those 20 cars in each set. And I would say those are successful tests, and I mean successful tests not because they proved our idea, but because they really was successful, and there was never there was mixing of cars, etc., some human errors. And as we can see, a team performed mostly always better. There was income update per car higher because for any of those relocations, then average distance was shorter. It means that you spent less electricity, less time, and number of relocations was smaller. What was very important, by the way, that both teams knew these sectors and potential income of sector. It means that if you're working manually, you still can look where is the best site. But still, the result wasn't as good as we could expect. Well, automated relocation was done smarter. And what was interesting, that average 18 income per car was higher, for example, for approximately 10 to 15%. Meaning that just by this example, we could rise at those moments income. However, again, if we like to extend, for example, 100 cars, that high number of city sectors, it could, we would have some higher computational resources, and probably if we will rise those resources, we still get to some level where we can't, again, compute it faster. And the problem is that you can't compute for a short period of time. You have to look in the window approximately to 1 or 1.5 hours, and then if you make longer this, then probability of this position changing in real time can affect your plan. So, and at the end, this is more like, at the moment for us, more about discussion that how we can look and maybe make things better. And ideas with further research is that we can look at the sharing interpreters. we may look at the car trading as a game. In this case, City is the whole game board. Game dices are cars. Then two teams of players, those who are customers. We don't know anything about the strategy, but we know that they're moving and using our cars. And then there's relocators who are trying to play against customers. And in that case, objective is probably should be keep potential income as high as possible in any moment. So it doesn't make long plans ahead. But if your allocator asks in this side and say, okay, which is the best car for me to take, system could show, let's say, that one and move that direction, that will agree. But those are just, let's say, discussion items and how to work, we will see. Thank you for your attention. I'm glad to see everybody is available.
Thank you very much.
So in one of your slides where you talk about the time calculations, you mentioned a maximum of 60 cars. And then in your conclusions, you were talking about 100 cars.
Yes.
And do you have an idea as to how many cars you will actually have? And I'm asking mostly because in another one of your slides, you were talking about 20-something relocations. I don't know if those are relocations per car.
No.
Oh, right, okay, because if you have 60 cars with 20-something relocations, that would be a lot.
No, okay. Let's, I'll try to, those 20 to 60 cars, this slide, we just try to understand how fast it works. Does it get optimal or suboptimal result for us? And it's clear that, okay, it's suboptimal. However, as it can be understandable, that if we increase this number and this number, then we need increase the number of allocators, those who are moving cars. However, well, probably not. But then this time, always we put 50 minutes as we set it as a maximum, and we will get some optimal results, but it will probably be worse than worse. In this case, we just tried to work with resources we have. I mean, Fitsi company resources, they have some, say, 8 persons who are allocators, and we can split them in groups and give some reasonable number of cars which they can work with. And they have approximately 100 cars in the city. And we took smaller group, 20 cars and 20 cars, so we can easily look after them, not just whole set. That's why these numbers are different. And this is movements per day for those 20 cars per team.
So normally if you run out of time as you scale the problem, then your alternatives are to use different techniques instead of optimizing, use some heuristic approaches, or you try and parallelize the algorithm, or you try and maybe use machine learning to find certain strategies to find heuristics or whatever it is. Did you try and look those?
Do you mean about optimization model, how it was solved?
So instead of using optimization, just use heuristics or parallelize these, because then you can.
Well, we used optimization model solver in the market. I don't know which exactly, but it was the work, teamwork. And well, probably there are some faster which could solve the optimization problem faster. Parallelization, I don't know exactly how it will go. However, it will still to get to the scale of numbers. Always have this multiplication combinations, even if we can parallelize it. If we can choose another model, probably, then yes, probably it can be done things differently. And that's why we are looking at the moment like this solution like looking at game, etc.
Sorry, I missed the beginning. I just want to make sure that I understand what you correctly. So you actually want to avoid probably the situation where all the cars are stacked one place in the city when there is no demand from. Actually, you could leave everything, the whole organization to be anarchy.
Yes.
So if there is a demand for a car and the car is being used, you understand.
Yes.
It's too close.
There is situations when it's best decision to do nothing.
Yeah.
That's true.
So
In real life, we haven't seen it ever. Well, except except weekends. The demand for cars is so high that they're taking for a long time. When they're in the center of cities of cars, there's not enough of them, and even those who are outside are always happy. But typically, there are some cars which, if you move them to the side, it will be taken in 30, 50 minutes, 15 minutes. If you side outside central, typically it's outside the center. However, it can be other way. Then it will stay there for probably 10 hours.
Yes, right. So, if I understand correctly, the relocators are real people going from place to place.
Yes.
In your algorithm, is it a central instance which does the calculations? Or, okay, so what I mean is, when the people who are relocating cars, you have two teams, automatic and manual. Yes? So the manual team, did the people who relocated the cars, did they make the decisions?
Yes. On their experience.
Okay. And your algorithm, was it working in automatic team? Was it working according to one central algorithm? Or-
Yes.
Okay, so there's this difference you can see. Yeah? So there's some potential for optimization here. Yeah? So perhaps if you could work the algorithm in parallel, like the real operators, perhaps it would take less time.
Yes, the problem probably is if you look at if you try to optimize the whole system, then somehow it was our decision at the beginning from this when we started to look after different algorithms or methods that were used, which direction to go. The feeling was that we can look at the system as a whole and try to this potential income increase for a whole system. It's not just for this car, but for the whole system. And then you have this central calculation question that you need to make this one optimization plan. If you look at, okay, I don't care about the whole system, how many cars is on charge, etc. But I'm here and I need to make the best decision. Then, yes, calculation probably is done like you said, like typically relocated. He opens the Mac, looks, I'm here, okay, it's 10 minutes for me to walk to that car, I will take it, I'll move it there, probably will be better. Then it can run in parallel, and then probably it is.
Yeah, I understand that it's a difficult thing to solve, but theoretically, if you could move it to an agent system, then you could reduce the time to take a decision and maybe keep the optimal results. Yeah.
Maybe, but you could have additional problems, for example, in parking spaces, because you have in some sectors, you have just a limited number of park space available.
Yeah.
And if you run it parallelly, all agents would decide to move cars to the center of city, and then you have the general problem because you have maybe hundreds of cars there, but not enough parking space.
It sometimes doesn't happen with real people.
No, it happens. By the way, it was one of the problems which we thought presenting And when they start work, I don't remember it was Thursday or not, they knew, as I said, this information about sectors and potential income for each hour. And they decided, okay, let's move. Okay, here's 4 cars, we have 4, let's take cars to that one spot. And oops, there is 8 cars. What can you do with that? There's no customers who need so many cars. They will need probably after 4 hours. So they exceed this limit of which we set for each sector, that there is some number of cars which is maximum. There's no higher requirement.
So basically what you need is a system in which actors are aware of each other's actions. So,
Yes.
By the way, who reorganized the relocate public transport?
Well, in our model, we expect that they're moving with the same cars. They may use this shared cars. Well,
That's one way, but how do they get?
typically, or they stay there and then move and walk, or which public transportation is fine. You can move in most of cities, I think, from point A to point B in 15, 20, 30 minutes. Almost everywhere. And other aspect is that if you're moving 2 persons in car, then the one who is driving is just waste of money. He's using car, and he's still playing himself.